Okay, in this video we're going to consider defining this line, this simple line y equals 2/3 x minus 1, parametrically in three different ways. So here is our line, right here, 3x minus, 2/3 x minus 1, quite simple to plot, of course, -1 y-intercept up 2/3, okay, and that's our graph. Now, if we are to define this parametrically, there are infinitely many ways in which we can define it parametrically. Okay, and so let's take a look at a couple of them, and let's take a look at the impact of redefining them each time. Okay, so the simplest of all parametrics to redefine this would be simply to consider allowing x to equal t and y equals 2/3 t minus 1. So that should not be that difficult to see how we eliminate the parameter there. It's simply a substitution. Okay. Now, um, of course, when we do define things parametrically, okay, we want to define it in some interval in t. Okay, and we're going to consider the interval in t from -3 to 3. Okay, now let's look at what happens. Okay, so if we look at the plots, okay, in x and y for time running from -3 to 3, of course, -3 goes in, and we get -3 in t, and 2/3 of -3, which is -2 minus 1. So we're getting -3, 3 at the outset, okay, which is our point down here where it starts. And then at 3, for t equal to 3, we're getting 3, and then 2/3 of 3, which is 2 minus 1, which is 1, 3, 1. So basically what we've done is we've redefined parametrically the line into a segment, the segment running from -3, -3 to 3, 1, okay? And so let's look at that in Desmos, okay? So taking a look at that in Desmos, here's our line, of course, okay? Y equals 2/3 x minus 1. And here we are defined parametrically, which you can see if I turn this one off, is simply that segment running from -3 to 3, 1. And of course, in doing that, we have motion along that segment as measured here. Motion along that segment as measured here. So this point is moving along this line in real time over an interval of 6 seconds. So we can easily come back and look at some simple computation. It's moved from the point down here, -3, -3 to 3, 1 inside of 6 seconds. So by distance formula, the distance between -3, -3 and 1, 3 is 3 minus -3, quantity squared over 1 minus 3. I hope all my arithmetic there is correct. So we've transversed a distance of radical 40 inside of 6 seconds, which is moving along this segment, okay, at roughly a little over 1 unit per second. A little over 1 unit per second. That was in what happened here. Okay, when we defined this parametrically on this interval, we defined moving on this segment, that piece of y equals 2/3 of x minus 1 from -3, -3 to 3, 1. So we did that inside of 3 seconds, which meant we traversed roughly about 1 unit per second. Now, I want to see if we can alter that somehow. So we're going to consider the following sets of parametric equations. Okay, we're going to consider allowing x to equal 3t, and y would be 2/3 of x minus 1, or 2/3 of 3t minus 1, which would be 2t minus 1. Okay, and we're going to consider that on the same interval from on the same interval in t from -3 to +3 on that interval in t, and look at what we end up with. Okay, so -3 input, of course we get -9 for x, and we get y is equal to, okay, -7. So we're starting at this point -9, -7 is what that should read, of course, and then we're ending up at 3 at 9, 5. So we're going from the point, we're moving again along the same line on a different segment, though, because our segment now traverses from -9, -7 to 9, 5. So if we take a look at that in our Desmos, okay, so now we're going to plot this, which, as you can see, is a longer stretch. Obviously, it's a longer stretch. And it's a longer stretch that it has to move in that same unit of time. So, of course, if we watch the motion of this in B now, okay, you're going to see that it has a longer stretch over the same period of time. And if we time that out with this, you'll see that we're moving in the green a lot quicker than we are in the blue. Okay, so so we've actually controlled the rate at which we're moving along this line, or along this segment, with our parametric equations. Now, so let's compute the distance that we traversed, okay, here. Okay, so we've moved from -9, -7 to 9, 5. Okay, so again, hopefully all my calculations are correct here. 9 minus the -9, quantity squared plus 5 minus the -7. So we're going to 18 squared plus 12 squared. We've traversed 468 units inside of 6 seconds, or we're moving at 3.6 units per second as compared to what we were doing here previously. So we are moving, okay, by altering those parametric equations as we did, okay, we're moving at about 3.5 times the speed of the original motion. And again, you can kind of see that going on here, that along the path in green, we're moving 3.5 times faster than we are along the path in blue. Okay. Now I want to consider one final interesting version of another type of yet redefining this parametrically. Okay. And in this case, I want to redefine it parametrically as such. I want to redefine x as 6 over t, and y as, of course, 2/3 of 6 over t minus 1. So that would be, of course, as you can see here, 4 over t minus 1. Now, obviously, we should find that this is undefined at t equals 0. Okay? So let's see, in fact, what happens here. Okay? Just plotting where our positions are, we're starting now at on the same interval from -3 to 3. We're starting at -2, -7/3, and 2, and ending up at 2, 1. Okay, so let's take a look at this on Desmos and try to figure out what's going on with this now. Okay, so now, okay, redefining this at with that sets of parametric equations, look at what we have. Okay, we basically have got a much much longer stretch to cover. We have a much longer stretch to cover. Okay, and so let's zoom out so we can see where that stretch is covering us, okay? Um, and we've got the motion on that in a whole different fashion. So check out the motion on this, if you will, okay? So we've got the interval where we're basically nowhere, okay? At t equals 0, so I want to drive that to t equals 0. At t equals 0, we're basically undefined. So you can see what happens. We jump across here, okay? Here we are at -1 and at 0, we're all the way up here. So we have a interval where we're basically undefined, okay? We have an interval where we're basically undefined in time. So the interesting thing that I wanted to illustrate here is a couple things, okay? Whereas, okay, one set of parametric equations by eliminating the parameter will yield you back to but one equation in x and y. So eliminating the parameter takes a whole lot away. It just gives you a very static placement, okay? So eliminating the parameter just basically defines what path it's taken. But when you have a path and you need to define it parametrically, you can parse that apart in oh so many ways, okay? And each different way is going to result in moving along the same uh, path or some portion of that path, okay? And with possibly different speeds and with possibly a undefined interval of motion, okay? So just some things to think about and to consider. So a lesson to be learned is this, okay? Um, a set of parametric equations by eliminating the parameter will return to you but one equation in x and y. A single equation in x and y, however, can be parsed into an infinite array of parametrics, okay? All with different conditions. So the thing is, you really have to consider what would be the most definitive way to parse those parametrics. I mean, we could do it as we see here, very trivial on a very trivial sort, or we could do it with a having great impact on the speed and grave impact on the intervals in time where position is undefined at some point in time. Very interesting. Okay, so yeah, you should welcome an opportunity to play around with some of those parametric equations using the Desmos. It can be a very interesting experience. Okay, there you go.